Okay, we're here at the Computer History Museum. It's June 16th, 2014. My name is Doug Fairbairn, and I'm here with Randy Bryant, who's come to share his experiences and career focused in the design automation and related topics. And we'll find out what else, if there's other things to cover as well during the discussion. Welcome, Randy. Happy to have you here.
Thanks. It's an honor to be here, to be interviewed. To be considered worthy of being interviewed. So,
well, you've been on a list for a while, so I'm glad we finally made it to work. What we like to do here is sort of find out where it all started and how you got to be where you are today. So that involves where you were born, what kind of family you were born into, brothers, sisters, especially in terms of how that may or may not have impacted and guided you towards your career choices. So let's start. When were you born? Where were you born?
So I was born in 1952, and I was born in New Jersey. My father was working for IT&T that time, which was a real electronics company. He was a microwave engineer. He'd gotten his PhD after World War II, and he'd met the department head's daughter and married her. So my mother was, my grandfather.
In what school was
at University of Illinois.
Okay.
So my mother's father was electrical engineer, professor, first at Ohio State and then at UIUC for many years. In fact, was the dean of engineering there.
So you come from a long line of PhDs and professors.
Yeah, well, his ancestors had all been Presbyterian ministers, so he's the one that really broke the trend and then set this other one of becoming engineers.
They all spoke from a podium, though.
Yeah, they all spoke from a podium. And so my grandfather just clearly was a big influence on my life. I mean, as a kid, we'd used to go down and visit Urbana-Champaign, and I thought it was the coolest place on earth with all the student union and ice rink and bowling alleys and stuff like that. And just the whole college life seemed great. And he'd take us on tours of various labs, and I just was really enamored by that.
So you really had it from the beginning.
I had it from the beginning.
That's
my mother's bachelor's degree was in physics. So.
Oh boy! It's the daughter of a
professor, although she did it more to get into journalism. So, and she'd sort of, in the classic mode of her time, sort of out of college, gotten a job, and then once she got married, she kind of set that aside to become a mother. But as soon as we kids, and then, oh, by the way, my father moved to Michigan, Detroit area, when I was about 3 years old, to become part of Bendix, which was aviation,
avionics,
electronics at the time.
But you were born in New Jersey.
I was born in New Jersey, but
then moved to Michigan.
Moved to Michigan.
Okay.
And I really spent from Michigan. I was there from there up through high school and then through college. So, and my mother still lives in Ann Arbor, Michigan. In fact. So,
brothers, sisters?
Yeah, I have two sisters. One's older and one's younger. Neither of them have gone the technical route. So, I was the family nerd.
Were you involved in doing electronic projects or anything?
A little bit of electronics. I more did mechanical stuff. I went off to college thinking I'd become a mechanical engineer, in fact. I mean, I liked electronics well enough, but somehow I liked more physical stuff. And my father had a pretty good workshop, and I built a lot of stuff and built go-karts and stuff like that. So but anyways,
so you had your path pretty well set.
What
about during high school or whatever? Were there any teachers that had a particular impact?
So I think the classes I really liked the best were math and physics, and I was fortunate. I went to a very strong suburban high school where they had advanced math courses, and especially the math teachers were very encouraging of us getting involved in these math competitions that were held within the state of Michigan at the time. And sort of got a group of, there were maybe half a dozen or so of us, all boys, who kind of clustered together and would study for these problems and stuff. And one of the math teachers, his name was Mr. Tumser, was very encouraging of that kind of stuff. And so that sort of combination, which I look at still today, the combination is sort of the theoretical math side of things and the practical building side of things, still kind of, I like that, and that's what I've found through my career.
Really served you well.
Yeah.
So it came time to go to college. What were your choices? What
Well,
were
I
your
really,
decisions?
really wanted to go to MIT, and I didn't get in. And I kind of wanted to go to Stanford, and I didn't get in. I got into Michigan and a few other places, and at the time, like, I was at this big suburban high school, so I think 74 of us from my graduating class went to Michigan. And to me, that felt like, oh, jeez, it's like
This is 68?
70.
70?
Yeah. Just felt too obvious, but of course, Michigan's a good school, so it was not an unreasonable choice.
Yeah.
But I really wanted to be more at a nerd school, quite honestly.
Was Caltech anywhere on your radar?
You know, I didn't even. I've thought of that often, that I would have done well to have applied to Caltech, and I don't think it even, for some reason, crossed the
Wasn't on your
on
radar.
my list. I think partly being more on the east.
Yeah. So you headed off to Michigan.
So I headed off to Michigan.
You stayed a major in engineering?
So I
or what
decided,
were you-
I was in the engineering college all along, and at the time they didn't have computer engineering. They had computer science, and it was part of arts and sciences. It was a bit quirky at Michigan at the time. And I like I said, I actually came in thinking I'd be a mechanical engineer. And a couple things happened. One was there was a mandatory course in Fortran programming. And I remember my first program was to convert from Celsius to Fahrenheit.
From what to what?
Celsius
to Fahrenheit. It must be everybody's first
Yeah.
program. Now that you
Where
mention
you
it, I think
literally-
that was mine too.
Where you literally were given the exact text of it, and the job was to key punch it in,
Right.
submit the deck with its 10 different numbers you asked to do the conversion for.
Right.
But I was hooked the moment I saw my cards get sucked into the card reader and then this roll of paper shooting out afterwards through the window of the computing center, because
Yeah,
of course no
of
one would
course.
get near to the actual computer.
Right.
I was hooked. And so that really triggered my interest. And I decided to major in applied math at Michigan, which at the time was a route you could take that was within engineering, but it was a little bit self-defined, and it was a little bit, let you go more toward computers.
Was that sort of the closest thing to a computer science degree, or?
At the time, I mean, maybe partway in, the electrical engineering department expanded and started providing a computer engineering degree. And for some reason, I didn't decide to switch over to that. But so I ended up taking courses in math, and there were some courses I had to take in various parts of engineering, but I did gravitate more toward the electrical engineering side of things. And in fact, I remember, speaking of hardware, the first course I took in hardware design with TTL Logic, of course, was by Dan Atkins, who's still alive and kicking and quite well known at Michigan. And again, I was hooked right from the beginning of that sort of hands-on. We were using PDP-8 MIDI computers, and the ability to write like interrupt handlers and see the thing responding to keyboard prompts and running, that sort of whole layer of the computer's running so fast that it can cycle through code and you hardly even notice it's happening. All that kind of stuff, I just really liked it. And so again, that sort of feeling of both hands-on and some theoretical basis to it, I really liked that.
So when you were, as an undergraduate, did you have a clear view as to what you were going to do afterwards in terms of graduate school or go to work? Or?
I knew I was going to go to graduate school. That was pretty clear to me. And partly, my mother got her PhD when I was in high school. So there I was, PhDs, both parents, grandfather's a professor. It's not a very big stretch to think I should go to graduate school.
Right, exactly.
And so somehow, let's see,
So I don't want to jump ahead, but I mean, what, I just wanted to kind of get an idea of what you thought you were preparing yourself for at that point.
I don't know if I remember, but I did have an interesting job between my sophomore and junior year in college. So this would have been '72. I went to Munich, Germany, and worked for Siemens in Munich, basically writing Fortran programs, and also programming a PDP-8 with a graphics display, and all that stuff. And I had exclusive use of it. I got that little key that you got to turn on in the morning, and I could program that.
That was yours.
And it was mine, and I had a great time.
How did you wind up with
Well, it was
Siemens
my
in
father.
Munich?
I wanted to be in Germany. I'd been an exchange student in Germany in high school, and so I wanted a job in Europe, and Germany seemed obvious. And quite honestly, my father arranged that through his company's connections. My father started his own company in the early '60s, a microwave electronics company. At a time way before people were generally going off and starting their own companies. So he...
No, that was a very interesting time. I've done some research in terms of what entrepreneurialism in the technical world at that point was, and it was pretty different than now. The world was
so
not
he
nearly
borrowed the money from his friends and family, basically.
Yeah,
got
the-
bank loans.
The
and,
venture capital world was not,
ah.
hadn't coalesced. There were people lending venture money, but it was not smart money. It was just people trying to find a way to leverage their dollars.
Yeah. And this was in the Detroit area, which was heavily dominated by the car companies.
Sure.
And very much, therefore, a union, heavy-duty union, white collars here, blue collars there, don't mix, all that kind of stuff. And it was in the era of basically the Apollo era. So he was mostly cranking out microwave electronics to be used in aerospace kind of applications.
Building stuff out of solid state, or is it?
Well,
is it all
his stuff, he was more the plumber, so building the actual cables and connectors,
I see.
all out of gold fixtures and
Yeah.
stuff. I actually had worked there 2 summers doing assembly stuff, just mindlessly tedious, awful machine shop kind of stuff.
made sure that you had no vision of doing that in the future.
Yeah, and I actually became, I had to join the United Auto Workers, was the representative of them. So that's a little bit of a reverse. But so through connections through him, quite honestly, I got this job at Siemens in Germany. And I had a great time. I enjoyed the work, and I enjoyed being in Munich. It was the same summer as the Olympics, although I left before the Olympics began. And it was kind of, I was like a little whiz kid. I was 19 years old at the time, which in Germany, if you were 19, you were still finishing up high school, typically. And I looked maybe 15, so.
And there weren't that many people programming computers at the time.
No, I mean, that was at an era when computers were still the sort of distant things you looked at behind windows. And this was a place I actually had the hands-on of this PDP-8. It was pretty cool.
Interesting.
So sort of with that, and so classes and summer jobs and stuff, it was pretty clear to me this is what I wanted to be working on, computers. And somehow the more hands-on parts of it I enjoyed as well. I liked I took a really good class at Michigan using some logic design modules that Gordon Bell had designed specifically to help for teaching digital design, where they were kind of in these larger chunks that you could assemble together. I remember, in fact, my
flip chip modules? Or they?
No, they were. I think they actually.
pre-
I've got the manual for it back in my office. I've kept it.
It's okay.
I don't remember much about them. I think they might have used some of the asynchronous logic coming out of WashU at the time. But I finished. I because of I'd gotten enough advanced placement and stuff that I could have gotten through college in 3 years, but I didn't want to get drafted. And so so it took me 3.5 years to get through college. But my last semester there, so that would have been the fall of '73, I took an advanced digital design class where we got to program 8008 microprocessor shortly after it had come out, and we could interface it with hardware. And I remember trying to develop as a class project a sort of rasterizer, graphics rasterizer, which didn't get it working. It was way too hard a project. But that whole business is sort of software hardware combination, and thinking about, well, you could put this in software, you could put this in hardware. And I really liked that. So, and I applied. So then I returned to Germany for the winter after I finished. But I'd submitted all my graduate school applications before then.
So the winter of what year is this now?
Winter of '74.
Okay.
40 years ago. In the summer of '73, I'd gone on a sort of road trip and visited Berkeley, Stanford, MIT. And I remember thinking Berkeley was sort of like a big Ann Arbor. It was a bunch of hippies. The whole kind of hippie culture. And it seemed like a pretty good place, but somehow I thought, I don't know. Stanford I really liked. I remember I hitchhiked from Berkeley to Stanford and met up with somebody who worked at the Stanford AI lab and lived in a commune. I think it was on the Stanford campus, and so I spent the night at this commune.
Do you remember who that was?
No, I have no idea. And but I should have, because he talked about this club they had building home computers, the Homebrew Computer
Oh, the Homebrew
Club.
Computer Club.
And about how, so he and these other people were talking about this, and I thought, well, why would you want to do that? But I visited the Stanford at the time. But computer science was part of arts and science. It was a graduate-only program. I remember visiting there. And then the AI lab was up in an old
Oh, I know where it is. I
Motorola
worked there.
place up.
Yeah, I went to Stanford and I worked there for part-time job during the school year and during the summer.
Yeah, so I went and hung out at SAIL some, and pretty weird people.
Yeah,
there.
that was
I remember
quite a good collection, though.
quite a collection of oddballs, which I really was pretty intrigued by.
Yeah, I was working there, and Alan Kay was working there, and so Alan Kay went to Xerox and had recommended that I apply for a job at Park, and so that's how I ended up. That's how I ended up at Park, through
Okay.
AI lab connections.
Yeah. So then I was off in Germany, and I got into all the graduate schools. So I applied to Michigan and Illinois. Those were like backup schools, and then Stanford and MIT. And I got into everything. So it really was Stanford versus MIT. And I remember my father going, "So you're going to MIT, right?"
Of course.
I don't know why he felt that way, and I thought, well, to me it was a little this and a little that. Okay, MIT, but I do remember that feeling like, well, I could go to Stanford. He had done a lot of business in the Bay Area as an electronics guy. In fact, he'd taken me to the Bay Area, and we'd stayed at Ricky's, which at the time was sort of the end of the developed world there, and beyond, south of Ricky's was all farm fields. So anyways, it wasn't like he was anti-Stanford, but he had a bias toward MIT. And so that's how I ended up at MIT. Arrived there in fall of '74. And it was a little of it was scary for me. Because my background was not really computer science. I'd done some computer science courses and some EE courses, and most of my programming had been in Fortran or assembly code. And
So you went in to get a degree in computer science? Was that the department?
yeah, I went into, at MIT it was all the EE department, but I was part of the CS part of that. It's all numbered. Course 6, area 2. All the MIT stuff is like that. So I got in there, I was in computer science, and also I felt there was a definite bias at the time at MIT of the people who'd been undergrads at MIT were sort of the people in charge. And even a lot of the faculty were MIT lifers. They'd been there undergraduates, graduates, and so it had this culture that was in some ways pretty inbred and pretty exclusionary. And so I came in feeling weak in terms of my preparation and stuff like that, but also really excited to sort of, being a nerd, to not have to do any more humanities courses, like focus totally. And look, obviously going to MIT was a pretty exciting prospect as well. So
yeah, for sure.
So I jumped right in, and I took a few undergraduate courses as prep, but I did just fine in courses. But I do remember at MIT, I linked up with a fellow there, a faculty member named Jack Dennis, who I was attracted to because he did sort of this balance between more theoretical things, and he was thinking about hardware. At the time, he was trying to devise a new class of computers he called data flow computers that were radically different from anything anyone was thinking of at the time. It turned out not to be a very good idea, but it was pretty exciting to think about being part of a change of reconceptualizing the whole idea of a computer. But I did find it hard, first of all, sort of coming up to a level of competence, and then I found the transition from being a course taker to a researcher to be difficult. And I've since learned that most students do it because their advisor says, here, let's work on this project, you help me out, and we'll get you on your way. And that didn't happen for me.
You say most professors now sort of help the students in that transition?
Yeah, they don't just expect them to sort of come up with a research
blossom into a research topic, right?
And probably I was on an NSF graduate fellowship, so I was sort of a little bit of a independent operator.
I see. You didn't have to.
I didn't have to
get somebody else's coattails to get funding.
Which was both a good thing and not so good thing in terms of having somebody for whom I felt beholden, and I'd get going and work on something. So I had a little bit of and this will be relevant as we talk later, sort of difficult time finding my way and sort of feeling like I'd really engaged.
How far into your time at MIT did you kind of come up against this?
Well, first of all, was coming out at MIT at the time, you had to get a master's degree, which included a thesis before you could get a PhD. So first was a master's, and then between master's and PhD, I had the same problem. So I'll tell you first the master's.
Yeah, please.
Fortunately, one of Jack Dennis's more senior PhD students came up to me and said, we've been thinking about the following research problem and thought you might be interested. And he said, we're basically building these data flow systems you can think of as a very large distributed asynchronous computer system. And they were building some hardware, microprocessor based, to create sort of a emulation facility. And he said, but we actually have no idea how to model these distributed systems on this hardware. Do you want to think about it? Might be a good topic for you. And so I went off and started thinking about it and actually came up with some ideas that were pretty successful. So my master's thesis was basically how to simulate one distributed system on another.
Sounds like a pretty aggressive topic for a master's thesis.
Yeah, it was. In fact, the thesis is still cited. It's like in my Google Scholar account, it's like my 10th most cited work.
Oh, wow.
And it turns out, I had this idea that anyone who thought about it very long would have figured out roughly the same thing. It's just that I was thinking about it before anyone else was thinking about it. And so that felt, and At the time, my advisor didn't even, and it didn't even cross my mind to try and publish a paper about it. Partly at MIT, to sort of over-exaggerate, there's such a attitude there that since MIT had really smart people there, in fact, all the smart people are at MIT. So you really don't have to publish papers outside of MIT, because look at, if you know, all the people who really matter are right here now. So you
Everything there is to know is being developed here.
Everything you
Right?
need to know is being developed here, and so just kind of here. And so I drunk that Kool-Aid and applied it, and sort of not getting much direction to saying, you know, this is such an interesting idea, you should take it out. So lo and behold, so I turned in my master's thesis, I think in '76, spring of '76 or so. And then a little bit later, my advisor was down at University of Texas talking to Mani Shandy and Jay Mishra, who were all excitedly telling him this new idea they had for doing simulation. And he realized they'd basically rediscovered what I did in my master's thesis. And fortunately, I had a tech report for my master's thesis that was actually, you know, a physically existing thing. And so Jack pointed these two guys to this thesis, and they were pretty bowled over. And quite kindly, they had a paper that was about to be published, and they put a footnote. They got the publisher to add a little footnote to the paper that said, we just found out that very similar ideas had been developed by blah, 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 and they gave a citation to the tech report. And so sometimes this is called the Shandy Mishra Bryant simulation method. And like I said, they could have said, it's a tech report,
Right.
what's this?
Right.
But they did, and they're very, you know, they're very generous in their about it, because I didn't feel like I'd really done much to promote.
Did you ever have sort of future collaboration with them or anything?
No,
like that?
and I never worked on this area again. You know, then it came time to get a PhD topic, and I could have taken the master's and turned it into PhD, but I couldn't really see where that would take me. And this was just an idea. It was purely a theoretical, conceptual idea. I didn't implement anything. In fact, there's a weird thing there in my group, at least at MIT. I think it was sort of a Edsker-Dijkstra influence that said, well, you know, real computer scientists don't write programs. We think about and reason about these things, but programming's no.
Develop algorithms or mathematical.
Yeah, it's all kind of this conceptual stuff, and which is really weird. So I didn't write any programs at all in graduate school until I got further along and interested in design automation, and therefore had to write some programs. So
I'm curious for other reasons as to, do you think that philosophy, or does that philosophy continue at MIT? Is that
totally gone? And in fact, I think everyone, everywhere, I don't know, most people everywhere really understand computers are this amazing tool that you can do all kinds of stuff. So even theoretical computer scientists write code, just, there's no point in trying to prove a theorem until you've run enough cases through it to give you a pretty good evidence that it's really true. So
okay?
I think that flipped tremendously. And that was just a kind of weird place. And I don't know how widespread it, I don't think it was, like the AI lab at MIT, they're all hacking code like crazy. But my little niche of it was more this sort of, we just think about it.
Okay. So you went off to do a PhD. So
I went off to PhD, and I was sort of running in circles and getting nowhere. Because I wanted, this is part of my own ego problem, I wanted it to be a big splash, because I'd sort of had success as a master's student. By the way, that at least the master's thesis kind of gave me a feeling like, okay, I belonged with this crowd now. So I was grasping at different topics here and there and trying to figure it out within the context of this data flow computing stuff my advisor was doing, and just not getting anywhere. And then that's when I heard about that there'd be a course taught by this woman visiting from Xerox on VLSI design. And so several of my office mates and I signed up for the course. So I believe that was fall of '78. And I love that stuff from the beginning. It just was perfect for me. We were using a draft version of the Mead and Conway
Yeah, no, I remember.
book.
I did help put that together.
Yeah, which is a pretty ragged book,
mechanical
by the way. You know, just to the first chapter by Carver Mead, I didn't have a clue what he was talking about in that one. And you know, it was a book. It was a book that was put out, and it was the right book for the right time. But it was a little bit of an uneven book.
That's okay.
And
so, yeah, well, go ahead. Who were the other office mates that joined you? And
okay, so they're all. Actually, it was quite a crowd. It was an interesting event because it brought in, at MIT at the time, the CS was in one building and the EE part was in another, and they're literally across railroad tracks from each other. And so I'd had very little contact in EE, more the EE side of things. And this course brought together an interesting collection of people who were coming at it from very different perspectives. It was really pretty fun. And Lynn, as you've probably seen, she has a whole website about this course and the students in it,
right,
all her projects, and she's carefully documented everything about that course. It's kind of
yeah,
fun.
she's totally anal about.
Yeah.
And but that turned out to be a very valuable thing that she did in terms of documenting all of her notes.
Yeah.
Because it became the mechanism by which it could be propagated.
I think she knew she was creating a legacy at the time. Yeah. And so what about the course? So yeah, my office mates included a fellow named Dean Brock, who's now in Asheville, a guy named Clement Lung, who's somewhere in the Bay Area. I've lost track of him. And various other students that it was fun because we all kind of like, and a guy named Andy Boughton, who's still in the Boston area.
So I'm just looking at the Lambda magazine, fourth quarter, where your article appeared on MOSSIM, and the other MIT contributors were Ron Rivest, Clark Baker, Chris Terman.
Yeah, I'll talk about them in a minute.
And and yourself. Okay, just wanted to see if it triggered any thoughts.
Yeah.
Go
so
ahead.
I'm not quite to that point yet.
Good. Okay, go ahead.
So the course was sort of, Lynn had taken everything and condensed it down, as I said, to red crosses green, and you got a transistor, and all the design rules and all that stuff. Which, in a way, was an amazing experience. And the way I often say, it was all one of the greatest lies in history, the whole Mead and Conway stuff. The lie being, anyone who's not colorblind can do VLSI design, right? You just need to know these rules and you can do it. The lie was, you don't really need to know all that electronic stuff, and it's pretty straightforward. And so it sort of got a lot of us into thinking we really knew what we were talking about when we didn't. And that naivety actually helped me, and I'll talk a little about how MOSSIM could come to an existence only because I was sufficiently naive not to know what was really going on. But Lynn had really turned it into this pretty nice curriculum that really only lasted about the first half of the term, and then the rest of the term the lecturers were just her friends from Xerox who came and gave talks. And then we were all working on our own projects, and so the four of us from my advisor's group worked together on a project which I don't remember much about, except that it was incredibly frustrating because we each were doing some part of this circuit, and we'd find ourselves in arguments. I thought you were putting a pull-up transistor on that line. No, it's your job. Oh, crap, we better put one in here somewhere. So it's like we're just completely, it was basically just seat of the pants circuit design, and the whole business of checking, is this a reasonable design rule checking. We didn't have any tools at all. Right. So I remember in that course project when Dick Lyons came in and gave a guest lecture, who was at Xerox, as you know, at the time, and he made this offhand comment. He said, we don't even really have tools to simulate these things. And I was thinking, he's right, and that's what's driving me crazy, is our group, if we had a simulator, some way to actually run this circuit through something, we could figure out that the pull-up transistor was missing. And so that little sentence, I think it was one phrase in this lecture that I don't even remember what the rest of the lecture was about, but got me thinking. And so after the term was over, I remember that winter break, I started thinking about, gee, I wonder if we could figure out a way to run a simulator. And I started to think about switch level simulation, the idea of modeling a transistor as just a simple switch, on or off. It's perfectly bidirectional. So at the time, the only people thinking about simulations, logic simulation, somehow I had to get it into a logic gate form, which meant you were propagating signals through gates, and not the idea of it just representing the transistors themselves. Let me turn this off. So, but one of the things that I think was implicit in the way the Mead and Conway was taught was it was all stick diagrams and all that stuff, that it was pure transistor design. And I think Carver had probably absorbed some of the circuit design lore at the various companies he'd been part of, Intel, I presume, to sort of pick up the idea that, hey, a lot of this stuff you really want to be down at the transistor level rather than the normal thing you'd see in a textbook, was that you'd start by building up logic gates and then you'd sort of be up there doing gate level design. So he hadn't really codified that part in the presentation of the book, but I sort of noticed that, and I was very intrigued just by that stuff. The other thing I'll say is that I was sufficiently naive that I didn't really know much more about it than that. I remember thinking, there's a rule that you couldn't, you'd get a 1 threshold volt, you'd get a threshold drop through a pass transistor. And I remember thinking at the time, it's too bad they get those threshold drops. I wonder if that's a problem they could fix or something, not realizing that they designed it that way on purpose. It was like, because I didn't really know what was going on. It's just this sort of
those switches.
Those switches, then too bad they're not better switches than that. But the whole idea that you could sort of mix ideas that really came out of relay circuit design with logic gate design and do all that stuff, it was kind of fun. And somehow I thought about the idea of switch, and once you start thinking about it, it's not that hard to come up with some starting of an algorithm for it. And I started to fiddle around, but getting back to, I hadn't actually written any computer programs in 4 or 5 years. And the only programming language I actually knew was Fortran, and nobody seemed to be doing Fortran. So I actually had to learn a local programming language being developed by one of the research groups around called Clue, and learn it enough to start writing code to even test out some of these ideas. And that was this huge change for me, to go from having this idea and trying it out, writing code, found that I could make it work. I tested out the circuit from my class project, and it kind of simulated okay, and went through the various examples in the textbook and got them coded up and simulating them, and so I realized this was going to work. And I remember Lynn Conway came back and had a dinner at the MIT faculty club for all the people in her class. And in fact, I ate prime rib. And I remember talking to her after the dinner was over and said, oh, I've been kind of had this idea coming out of the class of trying to model these transistors like switches and do a simulator. She said something like, well, that sounds really exciting. Please keep me filled in on anything you do. And that was enough of an encouragement to kind of keep me rolling. So that was the spring of '79. And I managed to ingratiate myself with John Allen, who was going to then take over in the fall of '79 and teach
the course.
The course. And I'd TA'd for John before, so I knew him already and had some credibility with him. But I told him partly, I've got this new tool and I'd like to try it out on the students because I think it would really help in their class to have this. And he encouraged me, and so basically I started hacking all these design tools for this course that was taught in the fall of '79.
So MOSSIM was the switch level simulator.
The MOSSIM was the switch level simulator that I came up with and wrote. So MOSSIM 1, which is described in that article you've got there, was the simulator I devised after taking a course from Lynn and getting it ready for this course in the fall of '79. And so that was my beginning of EDA, and it was really interesting because then in the fall it was a new collection of students, and John and I made up assignments using MOSSIM, and the students started using it, and I started getting useful feedback from them. And it was my first experience then of having created a tool that other people were using and realized I had to work a lot harder on documentation, making sure the tool had some consistent, high-level abstraction that you could understand what it was going to do without necessarily having to run the program. And it really started pushing me, in fact, realizing that I had to get ready for this thing had to be able to run on circuits that I wouldn't have thought of myself and had never seen before. And that whole attitude of, therefore, you have to have an algorithm behind it, a model and an algorithm, and it has to sort of implement that algorithm. And all those kind of things that, of course, are pretty standard ideas, really gelled in my mind at that point. It was really a lot of fun. So two of the people in the course were Chris Terman and Clark Baker, who then they already were in a group that was doing a lot more computer programming than I was, and they could program circles around me, and I got a little bit frustrated at first because basically Chris read the manual I'd written for MOSSIM, it's a 5-page manual, and basically wrote his own version. I go, how did he do that so fast? And then Clark came up with this design rule checker based on a sort of pixel level grid. Because of the Lambda design rules, you could assume you had a pretty coarse raster, and so he just came up with this idea of, instead of a line-based DRC, to do these pixel-based or raster-based DRC. And he, again, was this smart kid that could program circles around everybody, and so he and Chris and Clark came up with these tools that became the basis for that article they wrote there. And they got, if you remember that summer, some MIT guys went out to Park to try and create a Lisp machine on a chip.
Oh, yeah.
It started with a fellow named Guy Steele.
I remember that, yeah.
Had been in the course with me, at Lynn's course, and had designed the beginning of it. And Guy was an incredibly smart guy, and he'd written a bunch of his own tools. As I recall, though, he'd forgotten to put any metal over his contact cuts. There was something like structurally, fundamentally wrong with his chip that was so far off the mark that it would not possibly have worked.
Couldn't even do anything, huh?
Because at the time, DRC didn't exist.
Yeah.
And so one of the tools Clark came up with was a circuit extractor to go from the layout back to the circuit, doing it on this pixel-based idea. And again, if you think about it a bit, you can figure out an algorithm to do it. But it was the first, as far as I know, he was the first person to ever do that, period. Right?
Yeah,
and
very well be.
I remember because the VLSI book had this sort of correct by construction business that you shouldn't need to check back because your designs are correct by construction, right? There's sort of that attitude, again, this comes from Dijkstra, that had permeated at Caltech, because Dijkstra used to visit there, that, you know, said, we're such smart people, we don't need to check our work, because of course it's correct. We prove a theorem, and therefore there it is. So that idea was in some ways, I think, a pretty radical idea at the time among a certain set of people, that you should have to go from the layout itself back to a circuit. But he kind of closed that loop. That was, I'm jumping ahead, that was the fall of '79. In the summer of '79, Jerry Sussman and a various team had gone out to Xerox to try and design this chip, list machine chip, using the tools that you know of well, the layout editor and stuff. Icarus. On the Alto. And they'd basically, this is before Red Bull, but they'd just, you know, gotten through the whole summer eating junk food and drinking coffee and stuff like that, and came back with this almost complete design. And they ran it through these tools that Chris and Clark had developed, and found there was a power ground short. And Icarus, there became a term people called about Icarus that it could create mouse turds, meaning that you could drop a rectangle on something by just clicking on a button.
The mouse, yeah, sure.
And so there, you know, when they ran the circuit extractor and it said, "You got a problem, buddy," and they printed out this giant wall-size picture of it and went through it, you know, looking for it, and sure enough, there was this big fat rectangle that was connecting the, you know, they're all in the same metal layer, and there it was connecting power and ground. So that really, I think, was the moment of revelation for a lot of people, both collectively, MIT, Xerox, I don't know who else, that says, oh yeah, okay, we really need to get our act together on tools, and this idea of circuit extraction. And then the beauty of that is then with a switch level simulator, you close the loop back to the logical behavior.
Right.
You could simulate the thing in terms of zeros and ones, which was, at the time, in theory, we could have run SPICE on the thing, but SPICE was just couldn't handle more than a 20 transistor circuit at the time. So this was the idea that really closed that loop of, now we can go through the layout and then come back and make sure that we've actually got a working design. That was pretty, I remember Dick Lyon and other people at Xerox being pretty excited by that idea.
So got through that, you TA'd the course. What was the next major? Did you take that further, and did you want to say something more about the term you coined, the big lie?
I only really appreciated the big lie later in life, so maybe we should come to the big lie later.
Okay, that's fine.
So anyways, let's see, I'm trying to remember. Somehow it didn't really strike me that this MOSSIM could be a PhD topic, even though I was pretty excited by it. And I remember there was a meeting, again, there was a whole, as you know, a community building around VLSI that, not just at Xerox and MIT, but obviously at other places. And there was a DARPA program that got started to fund research at universities in VLSI, and that also was building up all the time. And of course, I was just a graduate student, so I didn't have the very top level view of all this stuff going on. But I remember there was a meeting that Lynn organized here in Xerox, Coyote Hill Road, that was bringing together various university people working in this, and I came to that meeting, and I remember just getting in a session where I was talking to Forrest Basket and various other people, and I described the algorithms behind MOSSIM, and just having this amazing exchange of, I felt like I had this ideas, and they were listening to me and asking questions and pushing me and questioning me, and that was pretty cool. And I visited IBM. One of my office mates, a guy named Glenn Moranker, had gotten a job at Yorktown Heights. He was actually in the same course we were, but he was a little ahead of us in getting through his PhD. So he'd gotten a job at Yorktown Heights. His father was also at Yorktown Heights, a guy named Will Moranker.
I'm sorry, his father was
His
what?
father was also at Yorktown Heights.
Oh, okay.
So Glenn invited me to come give a talk at Yorktown Heights. I'm having trouble remembering exactly what sequence things occur. And it was sort of a job talk, except I said I'm really looking for academic jobs. But it was a pretty good crowd that collected there. And I gave some kind of talk. Probably not very good. Well, it was about the same time I was on the job circuit giving talks at other places too. But I'm getting into this because after my talk, I met with Gary Hachtel and Alberto Sangiovanni Vincentelli.
Yeah.
So Gary at the time was working at IBM, and Alberto was spending the term or the year there on sabbatical. And Gary and Alberto kind of pushed me. They said, this is a pretty interesting idea, but everything you described is completely ad hoc. What is she really trying to do there? I said, well, there's no real model for this kind of thing because, it's not really circuits. It's all just ones and zeros. They go, well, you could have a model with ones and zeros, essentially something like that. Anyways, they kind of challenged me to come up with something that was more than, well, the program does what it does, and here's the algorithm that does it, right? And have something that you could actually. And so I went back and I don't know the exact combination, but somehow that became my PhD thesis, was to come up with a formal model of switch level circuits and an algorithm that would arguably implement this model and kind of put it all together. And that became my PhD thesis. And in the course of it, I much generalized and improved the actually very ad hoc and inefficient algorithm I'd used in the first MOSSIM. And but I didn't actually implement it. I just came up with this model and theory. But that was my PhD topic. And meanwhile, I'd attracted the attention of Chuck Seitz at Caltech. And he recruited me heavily to come to Caltech. So I went on the interview circuit, and I got offers at some
This
place.
once you'd completed your PhD?
No, I went on the interview circuit too soon. I was too optimistic about when I'd be getting out. So I went on the interview circuit in the spring of 1980, thinking that I'd be through by the end of 1980, which was completely unrealistic. And so I went out, and at the time the whole VLSI design stuff existed at a very small handful of the elite schools.
Right.
MIT, Caltech, Berkeley, Stanford, maybe University of Utah, just a very small collection of places had gotten. So mostly I was giving talks to people who'd never thought that it was possible for normal people to design chips. And so I just showed them pictures of chips, and everyone got wild and stuff.
Right.
But I wasn't really getting offers from really the top schools, except for Chuck really worked very hard to recruit me to Caltech. And I didn't really want to come to Pasadena, but I was, of course, very excited by Caltech and all that meant as far as, and here it was, like the center of the universe in terms of a lot of these ideas. So it turned out I took longer than I expected, and I didn't get my PhD done until the spring of '81. And I showed up at Caltech for the fall of '81, and that was the beginning of my time there. So it was pretty exciting in many ways, and a little bit disappointing in others, in that Caltech was an extremely small school. And I think there were 7 people in the computer science at the time. And Carver and Chuck were there, but both of them had various issues going on with their lives and were not as attentive as I'd thought. And but on the other hand, it was a good place to be. I made contacts. There was this industry-sponsored consortium called the Silicon Structures Project that had visitors from companies, Digital, Intel, Fairchild, all these companies that would come through for a year. And I met a lot of people through that became industry contacts that have continued for me. And in fact, I got there and I'd done this thesis of creating a new model but not implemented. And so my first task I really focused on was, okay, now let's implement it, and that became MOSSIM 2. And I had one of these SSP member companies was Burroughs, and so the visitor from Burroughs was a fellow named Mike Schuster who read my thesis, got really excited by it, and decided to help me implement it. And so we and one of Carver's students kind of dug in and implemented MOSSIM 2. And we implemented a programming language called Mainsail, which was a commercial derivative of a language called Sail from the Stanford AI Lab.
Yeah, VLSI technology.
VLSI technology did it. Somehow within this SSP, there was a sort of corporate decision to use Mainsail as a basis. At the time, C was a little too low level, and also we were still running on DEC 20 machines, PDP-10 based machines, and there wasn't really a C implementation. So.
And Mainsail was very portable.
And Mainsail was very portable. That was its feature, and it had garbage collection and all this stuff. And so yeah, we implemented MOSSIM 2 and Mainsail, and got it working. And Mike wrote or Mike, maybe some of the other SSP member company people wrote a circuit extractor and basically a set of tools on it. And the fact it was Mainsail became its greatest strength and its greatest weakness at the same time. So weakness meant there are all these people at universities who were dying for design tools, but and the company doing Mainsail, which was called Zydak.
Hadn't thought of that name for a while.
Yeah, XIDAK, remember that?
I remember,
Yeah.
I had a lot of business with Zydak.
Yeah, the world's a small place, isn't it? So the Zydak offered free licenses to universities, but in fact, Chris Terman and Clark Baker had bundled up their tools, which they'd written in C at a time when people weren't generally writing in C that much, and packaged it up and were distributing it widely to universities. And that I was in a little bit of a frenemy status with them, that Chris seemed to be getting this credit because his tools were out there and being used, and I thought I was working this more abstract, better algorithms and stuff, but I was writing it in Mainsail. And but the biggest plus on it was Intel also was using Mainsail for all their tool suite. And so for them, the fact it was written in Mainsail was a big plus. And they basically made a corporate decision to use Mainsail as their mainline simulator, logic simulator. Before that, they'd been using some hacked up gate level simulator that was trying to fake how you'd model pass transistors, but they knew that wasn't working, and they very quickly picked up Mainsail and put several people on the sort of software engineering, taking that code and making it ready for corporate, and building their whole design methodology of how they'd their whole tool flow essentially to
Around
have
MOSSIM
Mainsail,
2,
MOSSIM 2 running in it, And that was their main simulator for microprocessors. So that would have started in about '83, and it continued up through the 486, I believe. So I think the 386 and the 286 at least were run using MOSSIM 2 as their main simulator. So that got me on the road.
Okay, so you finished, so you were at Caltech, you finished up, you completed MOSSIM 2 in what time frame?
83.
83. So what picks up then? What's the next thing on your...
Well, a couple interesting things happened. I'm still at Caltech. So I sort of, because of this Intel connection, I really there's a guy named Rob Williner at Intel who left sometime in the 80s, but he was my main connection to Intel. And he kept saying, well, we'd really like it to do this, and we'd really like it to do that, and stuff like that. And they were very, very good customers, let's say. And they were SSP members, so they were actually providing funds to Caltech, and since half my salary was being covered, half my research salary is being covered out of SSP and the other half out of this DARPA program. So I felt pretty willing to work with Intel. And Rob got me into fault simulation, was something they needed. So fault simulation is, you imagine that you have some defects in your chip and you want to be able to run some, devise a set of test patterns that you'd run through your chips to detect whether there are faults. And fault simulation is just grading those vectors, running tests through and seeing what particular faults would it pick up. And so there's an idea out there called concurrent fault simulation that had been developed by a fellow named Ernst Ulrich at DEC, Digital Equipment Corporation. That was a clever way of, you could basically simulate the nominal circuit and all the variations created by as many faults as you wanted all at once. And that's why it was concurrent. You're running one simulation and doing it. And so this fellow Mike Schuster, who became my graduate student, he left Burroughs and became a Caltech graduate student, and I developed a fault simulator for MOSSIM. We called FMOSSIM. And that was a pretty frustratingly difficult, it was some of the hardest code I think I'd ever worked on, and still to this day. But it was an interesting experience, and we did actually get a paper out of it.
So at some point you left Caltech.
Yeah, so that's coming in, but I'm still not ready to leave Caltech yet.
Okay.
But actually there was, again, one of these little asides. Somebody somewhere, I don't even remember who in this case, said, well, thanks for this simulator, it's really good, but we actually have no clue what to simulate.
You mean what sort of vectors to
Yeah,
give
what
it?
kind of vectors? How do we actually know the circuit's correct if we can run this simulation until the cows come home, but there still could be some lurking bugs.
Right.
And that got me thinking about formal verification. And similarly, I remember, this is a funny story. In the in November, December of '83, I got invited to this workshop in Germany that was held in this conference center in the middle of the Black Forest that was called Oberwolfach, where they ran sort of mathematical symposia where they'd have people from around the world come, and you'd hang out in this beautiful middle of the woods kind of place and just have extended talks and discussions for several days about a topic. And so I got there and said, oh man, I need to sort of up my game here. Sound more mathematical than I really am. So I presented this sort of switch level model in the most abstract way I possibly could. And then I got invited to a German university after that as part of the trip to a university called Saarbrücken. And they asked me to give a colloquium, and I gave a talk about MOSSIM. And I thought, oh man, this code, I mean, it was really grungy and grimy code. If you really got into it, you could get excited by it, but it was really hard to get. It was one of these things. I've got to do something at this talk that's going to sort of at least give a glimpse of this as a future possibility. And I came up with an idea there. Oh, excuse me, I gotta watch my crossing hands. That somehow I could take this idea of concurrent fault simulation and then use it, rather than simulating a bunch of faulty circuits, use it to simulate a bunch of different inputs to a single circuit at the same time. I had this vague idea of a tree representation of all the possible values. And so it was sort of a hybrid of this idea of fault simulation, but morphing over toward symbolic simulation, wanting to run symbolic values through a circuit and seeing how it would behave over many collections of possible actual values. And this idea of a tree quickly morphed into a graph and basically became the basis of thinking about binary decision diagrams. I'd already heard about this idea of BDDs, and there's this paper written by a guy named Sheldon Akers where he posited these as an interesting way of representing Boolean functions, a graph representation, without any real algorithms behind it. But somehow that was in a different part of my brain. But as I was working out these ideas from fault simulation and concurrent, they kind of all merged together, and that's how this idea of using a BDD as a representation of these symbolic values and running a simulation where you're pushing BDDs through a circuit, and the core algorithm is then given the BDDs representing the possible values at the two inputs of I was thinking in gate level terms at the time, logic gate, what then is the BDD representation of its output? And that, through some weird collection of thinking about it, got me going in that direction. I was still at Caltech at the time. And but for various personal reasons, I decided I didn't want to stay at Caltech. I wasn't really enjoying Pasadena. Caltech had a lot of positives, but I felt it was too small at the time. I felt like I needed to be in a place where there was a wider range of people and things. And so I went on the job market and interviewed at several places, but Carnegie Mellon became the place I chose to go to next. And at the time I knew a fellow named H.T. Kung who'd been, the VLSI design crowd at the time was a pretty small bunch, and so we all kind of knew each other. So I had a connection into CMU that way. And then when I was early on at CMU...
So you went to CMU
So I went to
year?
CMU in the fall of '84.
Okay. And had you written sort of definitive paper on BDDs, or?
No. I'd written a paper about MOSSIM. I wrote a transactions on computers paper about it with the whole theory and algorithms and stuff like that. At the time, to get a paper through a journal took multiple years of refereeing and pipelines and stuff. So, and I wasn't, one of the mistakes I hadn't really gotten a good enough guidance on was the sort of hustle of publication. I was a little too laid back about it, quite honestly. But I had a few papers. I had a couple of papers at Design Automation Conference. I had this transactions. There's a series of conferences on VLSI design held both nationally and internationally, and I generally went to those and was giving papers on various different parts of it. So I was sort of in the crowd there, and people generally came to know the switch level stuff. But the BDD stuff, so actually I arrived in Pittsburgh in the fall of '84, and kind of holed myself up in my office and started writing a paper about BDDs. And that's a paper that was ultimately published in '86. And that's my highest cited paper. And for a long time, it was one of the highest cited papers in all of computer science. Still cite a lot of citations, several hundred per year easily. Citing as the sort of foundational paper on BDDs.
So can you sort of summarize the most critical breakthrough or insight or value that the BDDs
Well, I guess
provided?
what I'd say is I took it from what Sheldon Akers, and he did a predecessor at Bell Labs, which was just a sort of abstract representation of Boolean functions, and I built it into being a data structure with algorithms associated with it. That you had an API, an abstract interface that you could just say, okay, let's define some variables, A, B, C. Okay, I want to take the XOR of A and B and that with C, and now tell me if that's equal to some other thing. And so basically just thinking of these without even having to know what the data structure is, the ability to just assume you had some magic representation of functions that you could build them up based on sort of low-level logic primitives, and then you could do testing. You could say, are these the same? Is this output of this? One of the examples I did was take the bit-level ALUs out of the TTL catalog. Are those 2901?
2901 is bit slice.
Yeah, the bit slice where you can put them together and build. And then there was a 2902 was the carry logic for it.
Could be.
Right? And so you could basically build up. And so I showed that you could sort of take the circuit, they had a gate level circuit in the catalog. And then on the other hand, they had a table that says if this function is this, it'll add if it's an OR and XOR. And I showed that indeed the catalog was correct. I built up to a 64-bit ALU out of AMD parts, or I don't think it was AMD, TTL parts using the gate network.
AMD had the 2901,
Using the gate level parts on one hand and the documentation on the other, and proved that they were correct. And so, but that's really the main idea of BDDs, was it's this data structure, you can just use it, and it works well for certain classes of functions that are common enough to be useful. And so that was, the paper, the reason why it still gets cited is it's not like a least publishable units kind of thing. It was a paper that had everything, the basic representation, the set of algorithms, proved some properties, had some experimental results, showed that the whole idea that you're very sensitive to the order in which you declare the variables. You can get either big BDDs or small ones depending on how you do that. All that's in that paper, and along with sort of pseudocode to implement the algorithms and stuff.
So one of the important outcomes of that is progress in the whole world of formal verification.
Yeah.
It is sort of a basic building block, is that?
Yeah. Well, now they get used. That's jumping ahead a little. I'm sorry. This is going kind of slow, isn't it? I didn't really think it would take this long to talk, but. So then.
James, do you have any deadlines or?
Do I have deadlines?
Yeah.
No.
Okay, I just want to make sure we aren't running up against anything.
I'm going to make sure we have enough recording media. But
Okay.
Well, I have some
keep going.
deadlines, but
Keep going.
we'll
wanna
move
make
along.
sure. Yeah.
Meanwhile, at Caltech, this student of mine, Mike Schuster, and I had tried to formulate essentially a more symbolic way of thinking about switch level circuits, so that instead of just being able to run a simulator, you could algorithmically take a circuit and crunch on it and come up with something that would look more like a logic or a gate level representation. Not really logic gates, but something essentially an executable model that you could just feed forward. Take the state of the circuit, the input values, run it forward, and tell you what that circuit would do.
Mm-hmm.
And we'd basically spun our wheels thinking about it and come up with ideas, but at the core we didn't really have an engine, a way to, this sort of symbolic reasoning ability
Mm-hmm.
to make it work. But I actually had, so this is all kind of converging here, because I also met up with a guy at IBM named John Koch, who's the father of RISC machines.
Yep.
He was a character. I don't know. I hope at some point they were able to interview him before he died, because
Yeah, we do have some of him. In fact, we're trying to put together a team interview of the people that created the first RISC processor.
Oh, okay.
And some of them are still alive, and we're
Yeah.
trying to work the logistics
Yeah.
of doing that.
John Koch was a remarkable person, brilliant beyond brilliant, and but the goofiest guy you ever met. He'd be talking to you, you'd have a conversation, and he'd be talking about 6 things, and he'd sort of multiplex among them. And you just had to keep thinking, oh, now he's talking about error correcting codes. Oh, now he's talking about RISC machines. Now he's talking about compilers. He was an unbelievable person. Anyways, I guess people at IBM had been trying to figure out, well, he was the person behind a machine that they developed at IBM called the Yorktown Simulation Engine, which was an early version of a hardware simulation accelerator that worked. It was an incredibly naively straightforward and beautiful design of running. Just the idea of it was just to propagate signals through a network of Boolean operators much faster than you could even imagine. And they actually built this thing. And so John had been trying to, I guess some people at IBM and John had known about this, were trying to figure out how could we map a transistor simulation onto this YSE. And so somehow I got introduced to him, and he read my thesis. He read it in like 4 hours and came back and asked me more questions about the thesis than anyone else had. And brought me in to talk to people. So I spent like a week or 2 weeks at IBM in the summer of, it must have been 83. And again, I was trying to take this idea of coming up from a circuit up to something that would look more like a gate network, something that you could map onto the YSE and just propagate values through it and get it there. And that all kind of started merging together. So the BDDs were kind of one thing, and then this switch level stuff on another, and that all kind of merged together in the fall of '84 when I was new at CMU. And I came up with, I realized I could put this all together and came up with a program I called MOSSIM, MOSSYM, which I then presented at a conference of one of the VLSI conferences was in North Carolina the next spring. And I also presented at a DARPA program meeting, which was where all of us VLSI people got, and really that was the in crowd. And if you could present something that would get them excited, that was a big thing. And that was this huge breakthrough for me, was sort of merging the idea of taking a transistor circuit and being able to give it just pure Boolean symbols at the inputs and have it come out and say, yep, that's an adder, or yep, that's an ALU, or it could actually run simulations through multiple clock cycles and say, yeah, you've implemented this logic and stuff. Was my first entree into formal verification, and it was a really exciting step forward. And I remember just that feeling like I'd really cracked a big nut in doing that. So, that's spring '85. Let's see. Let me try and move things along a little.
Well, I was wondering, there's a thread here in the formal verification. I don't know what the is that sort of the major thread here through the next
And
10
that's
years?
really
or-
became my major thrust. I realized this is what I want to do.
That's who you were. So I'd be curious
And
as to what your view of it then was in terms of how quickly it could advance, or what the impact might be, or when the impact might be felt in sort of the real world designs. Did you have a feeling about that at that time, or was it too? And then how did your view, whatever it was, compare to how things actually developed? So the world of formal verification has been something that has seemed to have more promise or be
Yeah.
closer to reality than
Yeah.
turned out to be the case.
Yeah.
And I'd like to culminate in terms of.
well,
that-
so I think I always knew that this. So my version of this was, first of all, it was simulation based, because I'd come up. I wasn't trained in formal logic or any of that stuff, right? So I came at it from this more simulation view of it, and I was mostly trying to think of this both in terms of how would you actually use these tools, and are they going to work? Because the basic problem you get into with BDDs is if you can get the right variable ordering, they can be super, but if you get it wrong, you're in terrible shape.
in terms of the complexity.
They blow up, they have
explodes,
exponential
yeah.
blow up, and they just fail totally. And computer memory wasn't nearly what it is today, so
Right.
it would become completely useless. But I don't remember all, but various things kind of moved things along. So one was, I wrote a paper about BDDs. I wrote this journal article, but it didn't get published until '86. But in the spring '85, I had a DAC paper about BDDs that I used this 2901 based ALU as my benchmark to show that I could do it. And that got picked up by a few people, including a fellow named Fujita at Fujitsu, who then implemented this and came up with his own sort of heuristic way of getting variable ordering automatically based on just given a combinational circuit, trying to order the primary inputs in a way that you'd have a decent BDD. And he came up with some fairly straightforward heuristic for it. And then he went and talked about it to Gary Hachtel, who at the time was then at University of Colorado. And I'd met him before, but we weren't like buddies or anything. And then he came to visit CMU, probably to visit somebody else, and he came to my office and goes, I had this visitor from Japan who was telling me about this stuff you've been doing, and I'm pretty intrigued because I've been trying to solve this problem for years. And he started really asking a lot of questions. And then there was a fellow at Berkeley named Sharad Malik, who's now at Princeton, very well known, who also came up with his own. The time that Berkeley, Colorado were all kind of in cahoots with each other. And he came up with his own heuristic method for doing it, and they both published papers at ICCAD in '88. So I guess it took, this is a while afterwards. And that sort of broke open the whole thing about BDDs in the EDA crowd. That's when they went from being, they sort of went mainstream because that sort of opened up, they showed they could take a lot of circuits that were out there at the time, a lot of benchmarks, and do BDD-based stuff on it. There's another parallel thread that my colleague at CMU, a fellow named Ed Clark, had come up with this idea of model checking when he was, before he'd arrived at CMU. He came to CMU in '82. And he had some students working for him who I started talking to, one named David Dill, who's now a professor at Stanford.
Mhm.
And even though Ed and I were not working directly with each other, we kind of knew each other's work a little bit. And then he had a student come in named Ken McMillan, who is now at Microsoft. And within his first 2 weeks of being a PhD student at CMU, he came up with the idea of symbolic model checking. In other words, combining BDDs as a symbolic representation of basically sets and relations,
Mhm.
and then casting model checking algorithms in terms of these computations over sets and relations that would let you do things like, given a finite state system, but very non-deterministic, one where there's many possible behaviors. What can you ever reach a state where there's something gone wrong? The classic example, a traffic light controller. Can you ever reach a state where you've got green lights in orthogonal directions,
yeah.
right? Or for a cache memory system, can you ever get it where you access an invalid cache line,
Mhm.
a stale cache line, and you don't recognize it, and things like that. So Ken was an amazing guy, still is an amazing guy, and he was the one that really realized that this BDD stuff I'd been working on and this model checking his advisor Ed was working on could be married together, and that's where the things really took off.
Mhm.
And model checking is still today considered one of the real key parts of formal verification.
Right.
So that's sort of how at that point I really realized, this formal verification is stuff I want to do.
Mhm.
And I realized the advantage of working on hardware, there'd been work historically on more software-oriented stuff based on proving theorems.
Mhm.
That with hardware, especially since I was part of this crowd that worked directly from transistor level design, to be able to go up any level of abstraction and prove there was something useful coming out of that was a pretty big step forward.
Mhm.
And so I don't, you mentioned it's never been it's been a technology that's been a little bit tough sell from a EDA vendor perspective. I mean, but within companies like Intel and IBM, where they have a larger CAD group and it's more captive to the company and they're thinking things, it actually, some of these ideas got picked up pretty early. And so I spent more of my time sort of connected to these companies and their CAD groups rather than to EDA tool vendors.
So did you take on a role of advising or help start an independent company in formal verification?
No. Well, I mean, I've further down the road, yeah. By the way, I also then decided to do a redo of a switch level simulator I called Cosmos, which took these ideas of it. Cosmos stand for compiled simulator for MOS circuits. So it could take this idea of a switch network and run it through in this algorithmic way and derive a logic network that was functionally equivalent. And then you could run simulations of it that way, or you could run BDDs through it and do formal verification. And so I created this whole suite of tools. This was my early days at CMU. I had 4 or 5 graduate students. We all did parts of it and created this sort of whole major collection of tools, which I really at the time wanted to get it out to universities as part of my credibility. And that was my first time writing in C. I decided I had enough with these niche languages, time to go mainstream, so I went with C at the time. And that tool also then got picked up by a variety of companies, and including Intel, but also Digital Equipment Corporation, Hewlett Packard, and various others. And we licensed some of the technology in it to what was then Gateway Design Automation, which was acquired by Cadence. And as you know, Gateway was the originators of Verilog. It's where Chris Morby, is that his name? Yeah. Phil Morby was working. And they wanted to use these, there was a switch level model built into Verilog and they wanted to be able to do a better job running simulation and other things than they could. So we licensed parts of Cosmos to Cadence, or to Gateway, that then got incorporated into the simulator. So I was at that point I was part of the EDA community, pretty solid, very regular attendee at DAC, on program committees, editorials, journal editing, there's IEEE transaction type of stuff. So I was very solidly in the EDA community at that point.
So this is late 80s by the time these things evolved?
This is 90s.
90s?
Well, yeah, you're right. No, it's roughly late 80s, early 90s, right.
So what was the next major evolution? Yeah, we like to speed it up a bit, but I don't want to miss.
I know. So there I was a successful professor. I had graduate students. We were getting papers at DAC. We were getting papers at ICCAD. One thing I'd learned at CMU was to sort of step up my
paper publishing.
They had a sort of rule that you didn't go to a conference unless you had a paper there. So that
good motivator.
That motivated me, and being pretty successful. And that really kept me going for quite a while. The Cosmos was the main simulator used at Intel for a long, long time. And I always was very interested in being able to map onto hardware accelerators. There are fairly varieties of those at the time. So I dabbled in that a little bit. I was interested in testing. The fault simulation had morphed over to test generation, and used Cosmos as a basis for doing some of that work. So that became a sort of center, a platform on which I could build quite a few projects and have quite a few graduate students working.
So relative to my earlier question, whenever we talked about the whole startup evolution of Silicon Valley and so forth, did it occur to you that, hey, this is some stuff that maybe we ought to make a commercial product out of, and could we start a company? And is that a conversation you had?
Not really. So part of it was being in Pittsburgh. Part of it having watched how hard my father had worked and not really wanting to follow in those footsteps.
This is a good life.
I always said that sort of entrepreneurship, I claimed that we'd sort of jump generations, so that I was picking up my grandfather, which was really my mother's father, and he was the entrepreneur, and I said, I'm not an entrepreneur. Also, as you mentioned, it was clear that formal verification was extremely powerful in the hands of the right person, but completely useless for the ordinary folk. And if you looked at the EDA tools, especially in the early days, had to stay pretty generic in what they did and pretty predictable. And so they were mostly simulators, and then, of course, synthesis became a really big deal. And it wasn't, it was really hard. I could see that it would be really hard to get a formal verification tool that really connected. And the first commercially successful verification tools were equivalence checkers, right? That would compare, basically it was going from a Verilog and a transistor circuit and seeing if they were a faithful match to each other. Because at the time people didn't trust Synopsys. They'd run it through Synopsys, and Synopsys might introduce some bugs, and furthermore they'd take the output of Synopsys and they'd tweak it because they thought they could improve the circuit, and so they just wanted to make sure that it was
still had what they started with, right? Yeah. Well, what about sort of different tack here? In terms of your career at Carnegie Mellon, you were a professor, but then rose in the management ranks.
Yes, but I was still, all this I was pretty much your standard professor at this point. And then I became department head at CMU in '99.
Of the computer
science department. CMU has a computer science department inside of a school of computer science.
Oh, okay.
But I was sort of a senior and successful faculty member. I had some pretty major awards I got for the work. One of the papers behind Cosmos got the what's called the W.R.G. Baker Award, which was like a best paper award for all of IEEE for the whole year.
Wow.
Across everything they did.
Wow, that is a big one.
Yeah, that was pretty exciting. I was a fellow of the IEEE at a pretty young age for that, and I got an award. Ed Clark and I and Ken McMillan and one of Ed Clark's former students shared an award called the Kanalakis Prize from the ACM, which is sort of a theory and practice award, and it was because of symbolic model checking. So Ken having connected Ed and me, and then this fellow named Alan Emerson who'd worked with Ed earlier. So I was pretty well recognized. I was not, the work was definitely known at that point. So I became department head in '99, and I'd sort of steered more toward wanting to raise the level of abstraction and verification up, building on techniques that came more out of the world of theorem proving than came out of the world of low-level tools. And I'd have to describe that work as a mixed success. So the problem then, and still now to some degree, is that for most hardware design, the sort of Verilog model is the gold standard. It's the thing that people make sure that's the reliable model. And anything you try and get above that, if you try and have a separate model, then people start getting very uncomfortable because they're worrying about, are these consistent with each other? How do I construct it? How do I maintain it? And things like that. So I did work that was very interesting from a theoretical point of view and has had some practical impact, but not as much as, direct industry impact as this earlier work, of trying to sort of abstract more away from low-level Boolean signals and thinking in more high-level symbolic values. And that continued on, and I had a collection of graduate students who worked on that up through about 2004 or 5. And one thing that happened is I'd sort of split between the ECE and CS at CMU. My appointment was in CS, but I spent a lot of time, the EDA crowd was mostly in EE. And most of my ECE and most of my
ECE stands for?
Electrical and Computer Engineering.
Okay.
Which is a separate department, it's in the engineering college. Most of my PhD students were in ECE, a few in CS. We also came up with some interesting work on trying to verify arithmetic circuits using a variant on BDDs we called binary moment diagrams that seemed pretty exciting at the time, and there is some attempt to use them at Intel for verifying their floating point units. At about the time they started having the Pentium, if you recall, the first Pentium chips had a problem with their dividers, right?
Yeah. The floating point.
And basically, we did a proof of concept showing you could take, we didn't have Intel's exact circuit design, but ones of that general style, this general algorithm that was believed to be in there, and show that we could verify that both a correct design, and we could also show what was known about their 5 missing table entries in this table lookup algorithm they had, that it could have picked up those defects as well. And Intel, in some combination, took this idea and munged it around and came up with their own variation on a set of tools that to this day they use to verify their floating point circuitry. They rely on it completely. They don't even run simulations anymore of their circuits. They have all formal verification. So that was a little bit of a side thing, but also pretty exciting. And so there's a little bit of an interesting thing that happened in the formal verification world of the model checking, more bottom-up, purely algorithmic on one hand, and then the more classical ideas, which were from theorem proving, where you'd sort of basically try and prove a theorem that this circuit is correct, and you'd have a computer help you with that theorem, but it was mostly coming from the heads of the prover. But more and more they were realizing there's sort of middle ground between those two ideas. But this is getting further away from EDA, I feel.
Yeah, well, I don't specifically want to focus on EDA, but on your specific career. So
yeah.
Why don't we just, it sounds like things were mainly focused on the formal verification,
yeah, so
related
really,
things through the 90s, and
yeah,
did that continue into 2000s?
Really, from roughly 85 on, I realized formal verification was the thing that I was the most excited about. And I did various steps off of that were a little bit more, more pure simulation type of stuff. But the formal verification was what I was really excited by.
So where has that led you today? What's been the activities and focus over the last few years? And
let me just mention a few little things. You asked about companies. So there's been a few companies along the road that have started up themselves and asked me to be advisors to them. And the one that kind of connected the most directly was one called InnoLogic. It was started by some people from, I think from Silicon Graphics, that basically created a symbolic simulator. It would have been, if I'd done a startup, this would have been the company, right? A BDD-based symbolic simulator that could take transistor circuits and run them and prove various properties of that. And that company ultimately found a niche in verifying circuits like FPGA-based circuits with embedded memories, and being able to model because at the time there were no good tools that could cross that boundary between the RAMs of the available in the memory and their memory interfaces, and then the gate level circuits of the FPGAs, the logic part of the FPGAs, and they could handle all of this because they had switch level ability and BDDs working together. And so it was actually a modestly successful commercial product and was acquired by Synopsys, and is still available. There's a Synopsys product that uses this today. Similarly at Cadence, I said they've licensed various parts of the technology along the way. Several of my graduate students have gone to work there and built up, and they again have formal verification tools that they've built up from various different pieces of stuff merged together, but there's little chunks of my DNA lurking in some of those tools. So I'd say they've had impact on the EDA world, even if I've never been directly doing my own company.
So Cadence just acquired Jasper. Was Jasper have any of that?
Jasper has it. I don't know much about Jasper.
Okay.
As you know, once you get going with one company, you're kind of excluded from others. So, and actually I have some students who've gone off to work for Jasper. I've known various people there, but I've never been directly involved in the company.
Okay. So where do you find yourself today? I mean,
well, since 2004, I've been the dean at CMU, and that's really taken me away from being down in the trenches doing hardcore research, quite honestly. When I first started, 2004, so 10 years, I'm just finishing up, by the way, into this month. I'm no longer a dean. July 1st,
is that
I'm no
good?
longer dean. Yeah, it's going to be good to change. 10 years, I think, is long enough to do any one thing.
Yeah.
And so, let's see. So, into the beginning of Dean, I still had some graduate students working away, doing more high-level kind of symbolic reasoning, not just hardware, but these ideas actually apply to software too. And so, for example, one of my students works at Microsoft doing software verification based on these. Another one of my former students is a fellow named, his name is Shivendu Lahiri. Another one of my former students is at Berkeley. His name is Sanjit Seshia, and he's a successful tenured faculty member there doing work that's built on, some of which is related to work that we did earlier on. So those ideas live on, but I haven't directly done research in that area for 8 years or something.
So let's talk about deanship. What you came in as a dean, what were the challenges? What was your vision of how it?
Well, I had the
involved, and what was
luxury
your-
at CMU of becoming dean of a very strong place that was very well established before I began. So computer science really started at CMU in the mid-50s when it was just a sort of backwater rust belt, before there was a rust belt.
Before it was rusty.
Before it was rusty, smoky, technical school. But this fellow named Herb Simon, well-known person, came in and recruited a protege named Alan Newell, and they basically started a lot of artificial intelligence work came out of them. There's a fellow named Alan Perlis, who was early on in programming languages, the first winner of the Turing Award, and the three of them started the computer science department at CMU. At a time when CMU, it was actually called Carnegie Tech at the time, was not a world-recognized place. But these men, they were men, had this vision of computer science. They wrote an essay in Science magazine basically arguing, making the case why there should be a discipline called computer science. And one of the things they did that I think was unique was really project computer science in this very broad terms. So they said computer science is the theory and design of computers as well as all the associated phenomena. So you can think of theory and design of computers, hardware, software, that's kind of the normal mix you think about, but the phenomena kind of provided a charter to think about this as not just being machines that you build and program, but also robotics. Alan Newell did a lot of the early work in human-computer interaction. A lot of work in artificial intelligence, and it sort of blossomed into this very expansive organization. So I really came at it much more from the hardcore computer systems, hardware viewpoint, but most of CMU is where I think it sort of strikes its biggest impact is more on the AI and variations of AI, computer vision, speech recognition, self-driving cars, all those things that have really blossomed in the last, just the whole field of this has.
Sure.
And I think they also, if you think about how pervasive computers have become for us and how they're involved in everything we do and they mediate every interaction we have with other people, those are all the phenomena that have made it possible. So in a way, I just was lucky that I had landed in a place that had this vision, and it became one of the first universities to have its own separate school of computer science, separate from an engineering college or an arts and science college. That started, actually, we're in our 25th year of that right now. And I was the fourth dean. So it wasn't like I had to do a lot of new stuff. And I feel like that 10 years, it's just a time when the whole field is expanded and exploded. In the depths of the dot-com bust, we only were getting 1,700 applicants for our undergraduate program, where we wanted only about 120 students coming in, so that was okay. But now this year we have over 6,000 applicants for that program.
For how many slots is it still?
142.
140.
So. It's crazy.
Amazing.
And so it's been pretty exciting. I'd describe it more as a ride than, of just being there and at school where it's, I'd say I had some impact around various margins. One of the things that I got very excited about starting in 2007 was big data, what we now call big data. It wasn't called it quite then. But partly having visited people at Google, seeing how they ran their data centers and sort of the systems end of it, and then all the, what you could do with more and more information. Our language technologies people came back from a competition they'd had organized by NIST in language translation, translating between newspaper articles from Arabic to English and Chinese to English. and they'd just gotten their asses kicked by Google. And the difference was Google wasn't particularly clever algorithmically, but they trained their translator on 1 trillion words of text and dedicated 2,000 node cluster to it at a time when everybody else was several orders of magnitude less than that.
Yeah.
And it just showed that there's some problems that you can try and be clever, you can try and be big, and sometimes it's
big is better.
Big is better. and Google has an interesting presentation they could give where every time they doubled the size of their training data set, they got a little delta in the quality of the speech translation, and that was their key. So these people came back and says, you need to get us a 2,000 node cluster so we can compete against Google. And so that kind of got me thinking about this sort of bigger picture of, wow, this is amazing, mostly being driven by industry, and the academia seemed to kind of behind the game of really thinking about this. So I was able to organize both within CMU and a little bit at a national level, sort of thinking about what it would mean to pull this into the universities. And the National Science Foundation set up a funding program, and we formed a connection with Yahoo that let us get access to a 2,000 node cluster they'd set up for university use. We were the first university to be able to do it. Was literally a shipping container on a parking lot of one of their Sunnyvale facilities filled with machines. And it had been something they'd acquired as an experiment and decided not to use as a company, but they said, hey, we could kind of get this going and let some university people get in and start using this. So
Interesting.
So that sort of, I would say I had that impact at CMU of trying to rally the troops, because we have everyone from the low-level computer systems people to machine learning to language technologies, computer vision, the sort of people that want to use this stuff, and the people developing it, and then more algorithms, programming languages, machine learning in between. So it's been a big part of my focus.
When we try to wrap things up then, one question we like to ask is, if you put yourself back as a undergraduate and trying to figure out what you were going to do, what would you pursue today? Would you follow this path you're on? Are there things, where do you think the opportunities?
Well, the thing that, I purposely got away from EDA thinking that I think there are more bugs in software these days than hardware. So
Clearly.
I think
by many orders of magnitude.
And it's a lot harder problem, software verification.
Yeah.
So a little bit, I morphed myself a little bit more toward the software side of things, and I still think that's a huge research area to work on.
Well, especially with self-driving cars and all this other
all
autonomous
this other
stuff out
stuff
there, right?
that we really
You'd like to have some confidence that it actually
works.
Yeah.
Incredibly hard problems, because how do you even formulate a model of what a self-driving car might encounter, and therefore that it should deal with, right? It's really a hard set of problems. So if I were to go through it all, obviously I felt like I've sort of stumbled and had a lot of lucky accidents along the way, but I've mostly felt fairly fortunate about how that all progressed. And I will say that there's a lot of people along the road who've been, like I've mentioned, just a small comment here or there, a little bit of encouragement. I still remember those, and they had a pretty big impact on me. And I think people have been very generous with their time and attention on me, and I appreciate that. And I like to think I've been able to do that for some other people as well.
All right, well, that's a good note to wrap things up on. Thank you very much for spending a couple of hours with us.
We didn't talk about the big lie. Should we talk about the big lie?
Yeah, let's talk about the big lie. Sorry, we definitely need to go back to that.
Okay.
Please do.
So I joke about this, but this is just my way of doing things, that the whole Meade-Conway business was a big lie, meaning that it's sort of this idea that, as I said, is if you're not, as long as you're not colorblind, you could do transistor circuit design. So for example, I remember this article by Ron Rivest. RSNA, Rivest, Shamir, and Edelman tried to design their own chip to do RSA encryption and decryption. And they really worked their butts off on the chip, but it had no prayer of ever working because they didn't know circuit design. So for example, it used a DRAM circuit called a 3-transistor DRAM that I later learned basically never worked for anybody. And they didn't know that. I was only distant. I wasn't really directly involved in their project. But on the way, Ron thought of some interesting ideas for routing that became an algorithm he did. And so there is a whole bunch of people doing chip designs that didn't really have a clue what they were doing. But it brought in this whole collection of people from very theoretical to people like Hennessy and Patterson and Randy Katz and that whole crowd there, Berkeley and Stanford, that, and then the whole EDA business in many ways, parts of that, I think would have happened already. I think the Berkeley crowd, the Newton, San Giovanni, Vincentelli crowd, they were already sort of pretty well connected to the electronics industry, and that might have gone on its own, but other people, I never would have gotten involved with it if it hadn't been for Lynn Conway and the Mead and Conway stuff. And I think it did have this effect of really pulling people up out of the mire and thinking much more abstractly about what system design meant and what it meant to design systems that had to map to the sort of two-dimensional structure of chips and all that.
Yeah, I think, as I said before, I have a very similar take on it. I was in the middle of it and had some of the, having an electrical engineering background, realized that there were some compromises and shortcuts taken and so forth. But on the other hand, the impact through bringing, using the notes that Lynn created at MIT, along with the book, along with some videotapes that we did and so forth, I thought it was, to me, the most amazing thing was watching this idea, revolution, whatever, spread to hundreds of universities within a very small number of years. And whatever the missing pieces or little lies or big lies or whatever that were being told, the actual impact was the education of thousands of students in terms of a high-level view of an incredibly important area, who then came to populate the semiconductor, EDA, computer science, companies, universities, each of whom developed the additional knowledge to do things completely and make real working chips or real working tools. But it was it provided a step that everybody could get excited about and get involved in, and then it was time to learn more. But it was an incredibly important launching pad.
And it was done in a way. I mean, there are some number of old school people who said, "Oh, stuff's a bunch of baloney." But
very large number.
But there were enough people, like Carver, who were, I'd say, more enlightened. They realized it was way harder than this, but they could communicate effectively. And you look at the places like Bell Labs, that really picked up on these things. There were groups of people got together and educated each other in many different ways. And the whole tool business, I think the idea of a much more tool-oriented approach to it was part of what came out of that too. So it was pretty exciting. So it was
absolutely.
And it's amazing to think about how all that converged, what a perfect timing it was. It was at a time when there was a relatively stable NMOS process called HMOS, remember? That was fairly standard across the industry. The chips were small enough that you could big enough you could do interesting things with them, but small enough that it was hard. And everything was just right on the verge. So, the idea that this simulator I developed with a student then became the mainline simulator for Intel.
But that was an indication of, you know, the importance of getting people with that kind of background,
Yeah.
that kind of perspective involved. Even
Yeah.
if you didn't know all the details, there was a huge gap in terms of who was participating
Yeah.
in the world of chip design. There were, you know, very skilled but very narrowly focused circuit designers, and they weren't going to get where we needed to go
Yeah.
without the help of computer scientists such
Yeah.
as yourself.
No, it was really it's just, I mean, I call it the big lie, but it was an amazingly successful
Right.
time. It just, and then DARPA built up a big program and
Mhm.
and NSF built up a big program. So there was real money behind it, and that's critical in a university to really make people
Right.
put down whatever they're doing and start something new. There has to be funding or it just doesn't happen.
Right.
And as I mentioned, the DARPA program meetings were, to me, that was the members of the fraternity. That was where you really made your mark on who was the who had the best ideas at any given time.
Anything else we've left out?
That's the main one.
All right. That's a wrap. Thank you.